So thanks for inviting me to speak about this subject. Field transformations in functional flow equations are, in my view, an important topic. It's quite powerful. You can do a lot of things with it. It has found already wide applications. I think the earliest applications have been with composite fields, the mesons in QCD, or antiferromagnetic spin waves in the Hubbard model, or the relation between composite and fundamental fields, more general. And of course, this relation between composite and fundamental fields can depend on the renormalization scale K. And as a result, you get correction term to flow equations. Another important topic where field transformations have been used are dressed fields. Also, the simplest thing is renormalized fields, scale invariant fields, and so on, more generally incorporating some type of wave function renormalization. And I think a lot of recent discussion has come with the so-called essential RG. You can, of course, obtain computational simplifications by transforming away some couplings that get you into trouble because they are too complicated for following them explicitly. That seems very promising. It is promising, but it's also dangerous. And about these dangers, I will talk today in order to make you a bit aware of what I think one can do and what one should perhaps better not do when one speaks, when one transforms away couplings. One of the advantage of using field transformation is also one may get for some circumstances better insights into symmetries. For example, by formulating a cutoff for composite fields that is consistent with symmetries, where there is no such cutoff for the fundamental fields. Well, my task today is not so much, giving you nice examples for the use of flow equations. I think there have been plenty, and that is not my aim today. Today will be a somewhat technical talk. Because I think the subject has a lot of potential, but there are also some claims and directions that have a certain danger, and I want just that the community is aware, perhaps a bit more aware of these dangers, what can happen, and what one should perhaps better think about before making too strong claims. So let me start with a simple subject, linear field transformations. That's pretty straightforward. There's a standard example used since the beginning, renormalized fields, where we make a linear field transformation by factoring out a wave function. You can, of course, go then to scale invariant fields that you use if you look for scaling solutions. All that is well known in the community. Also, what is often used is momentum-dependent field transformations. This is still a linear field transformation. You just transform different Fourier modes separately. So your linear transformation is momentum-dependent. And that can be very useful if you want to simplify the propagator. And it can be very useful if the momentum dependence is sufficiently smooth. That is if the momentum dependence is sufficiently smooth. Because I give you a simple example where you better do not do it. Let's go to the Fermi surface in electrons. Fermi surface for electrons in solids you can transform it completely away. And that is probably not a good idea. And the theoretical reason is that it gets complicated in position space, but let's just go through it very quickly. So if you have solid electrons in a solid, they have a typical inverse propagator, which depends on a function of momentum, epsilon of q. That's where the information in the surface, the Fermi surface is stored in, the chemical potential and the temperature with the corresponding Matsubara frequencies. So now I can easily make a regular linear field transformation. I just transform every momentum mode by square root f of q. This should not have a zero such that it's regular. And by this field transformation, I can immediately transform my inverse fermion propagator to q squared over 2m plus a temperature-dependent part. So what has happened? It's now a free theory. You can also keep a chemical potential if you want. The Fermi surface has completely disappeared. And you say, well, that doesn't seem to be such a nice thing because a lot of physics is in the Fermi surface. So where did it go? Well, you have moved by this type of transformation, the physical information on the Fermi surface, you have moved it to vertices. And it's, of course, much more difficult actually to refine, to take out again from complicated vertices the simple information that has been in the Fermi surface. So already at this point, I think we have a pretty important lesson, namely that couplings that can be transformed away, they are not unphysical. So some people call such couplings that can be transformed away, they call them irrelevant. And I've often heard the statement that irrelevant couplings you do not have to care about because they are not physical. This is simply not true. The so-called irrelevant couplings are, of course, physical. The momentum dependence in the Fermi surface can be transformed away, but this does not mean that there is no physics in the Fermi surface. So the field transformations, the only thing they do is they move physical information between different sectors of the effective action, or more generally, if you look at flow equations, they move physical information between different sectors of the flowing action. So that is a very general statement, because if you think about observables, observables are not just correlation functions of fields. Observables are always a pair of a choice of fields and function of these fields. And if you make a variable transformation, you go, of course, to a new choice of fields. You go to new functions, to new correlation functions. The observables are invariant, but of course, you can do a lot of things by these type of field transformations. So let's go now to nonlinear field transformations, which is the main topic of this talk. So for, oops, why does it not work anymore? Okay. No, it works, okay. So nonlinear field transformations are even much more powerful than the linear field transformations. And I have marked a little bit the too powerful tool for effective action and flowing equation. Two is, of course, only if you do not apply them correctly, or if you're not taking care of important things. They are a really powerful tool. There are many possibilities. For example, by nonlinear field transformations, you can transform completely away the potential in the scalar field theory. I will give you an example for that. Transforming away means, again, information is just shuffled to other sectors. And while field transformations are exact, truncations in general, they can become very misleading. I'll give you an example. We had an example already. If you transform propagator of fermions that contains the information about the Fermi surface. If you transform it to a standard propagator, that's all exact, all fine. Now, the information is in the momentum dependence in the vertices, but if you have now a too crude truncation for the vertices, what will happen is you simply lose the physical information. So the real issue is not that field transformations are unexact. They're all, if you do things correctly, they are just exact transformations. The real issue is are the truncations. You do not really want to transform important physical information into sectors that are much less accessible and where you then have much less resolution on truncation. That's the real danger, and that is what you also should keep in mind for gravity, where we often do not have a very good oversight on many correlation functions and their behavior, and where if you're too crude, it's easy to make errors. So the simple lesson is better keep track of physics. You should not be satisfied by having simply an exact, formally exact information, but you should really keep track of physics, of what a transformation does. Next topic is that we will see that there are different versions of field transformations, which I call microscopic and macroscopic field transformations. And I will explain you more in detail in what is coming, where the differences are, where the respective advantages or disadvantages are. The microscopic field transformations, they just transform the fluctuating field variables in the functional integral. They can be combined with new sources and new cutoff for composite fields in the flowing action. And that goes back to Jan Pawlowski and the essential RG. That actually uses these microscopic field transformations. You may be a little bit skeptical because you have not seen variable transformation in the functional integral for deriving these microscopic field transformations, but you will see in a moment that it's nothing else than that is actually behind it. In contrast, the macroscopic field transformations, they transform field variables in the effective action or flowing action. So these are simple variable transformations in a given functional integral. If you go to microscopic field transformations, you have, of course, a Jacobian. You have a field transformation in an integral, and if that is nonlinear, you necessarily get a Jacobian. Well, often the actual formulation of the field transformations in the flowing action does not use field transformations in the functional integral, and you may not see immediately this Jacobian, but I will tell you it comes back. It comes back through the initial conditions, even if the integration variables in the functional integral are kept fixed and only sources and cutoff are changed. And actually the correction term in the flow equation can be interpreted as a k-dependence of the Jacobian. In contrast, macroscopic field transformations, there is no integral to be done. They have, of course, no Jacobian. This Jacobian is sometimes thought to be more or less a trivial thing or something that is, well, it's annoying, but people do not worry too much about it. But the Jacobian often has a lot of the physics in it, and that should not be forgotten. I make you a simple example, a scalar field theory with a single scalar field, and with a classical action that has a kinetic term where the wave function renormalization k of chi, or I often call it the kinetical in analogy to the potential, is a function of the scalar field. That's all. So that's the action, the classical action. Then you have, of course, as usually, a probability distribution associated to it in Euclidean or a corresponding object weight function in Minkowski signature. you have the partition function, and the partition function involves, of course, a functional measure, and the functional measure is taken here to be linear. So it's just an integral over the scalar field at every point x. Now this model is a model with interactions. You see that immediately if you solve the field equations, then you see that it has terms that are not linear in the fields. So it's typically a theory with interactions. Now let's go to a microscopic field transformation of this simple theory. Well, you take phi prime of x, you take a function of chi prime, you take it such that d phi prime or d chi prime is the square root of k, and then obviously this action with this non-trivial kinetical becomes just a free action with d mu phi prime, d mu phi prime. Well, this does not mean that we have all of a sudden that the theory is equivalent to a free theory. But the whole physics that makes the difference is actually the Jacobian. Because if you look at the partition function, d chi prime e to the power minus s, that gets, of course, when you write it as a functional integral over phi prime, it gets a Jacobian g of phi prime. And now you have the e to the power minus s, that's the same, you just insert your field transformations chi prime or phi prime. So this part here, that gives this free theory. But the Jacobian gives you, if you want, an additional piece to your classical action. You just subtract from the classical action the log of the Jacobian, and you get a new action. Now this new action is not a free theory anymore. In this case, the Jacobian is relatively simple. It is just this derivative of chi with respect to phi, local function. And if you write it down, you can write it as a potential. So it's the integral over x, the log of d phi over d chi. And it has a prefactor, epsilon to the power minus d, that comes from the fact that you have somehow to specify what you mean by this product over all space points. You can put it on a lattice if you want, and this epsilon is essentially the lattice distance. That sounds harmless, is in practice often pretty annoying, because otherwise you would say, okay, I just take the Jacobian as it is into account, and that's it. But in practice, you see, if you really want to do this procedure with the explicit Jacobian, you need to specify how you regularize it exactly. And that makes, well, this can make things pretty cumbersome. So conceptually, it's very simple. You have integral, you transform variables, you get a Jacobian, and the Jacobian, once you write it again as a linear measure here, it just modifies your classical action. So this Jacobian in this case gives you a field transformation induced potential. It's just given by the log of k of phi. This gives you the potential. You have these two completely equivalent transformations. That sounds harmless, but I told you already that all things that depend where you remember that this theory with a non-trivial kinetical was an interacting theory. This is, of course, still there. And in this case, it's now in the potential. In the potential, you see it easier. For example, you may have a kinetical that has this particular form. Don't pay too much attention to it. It gives you then a corresponding potential. And this potential has a minimum at phi 0, at phi prime different from 0. So it has classical spontaneous symmetry breaking. So in this theory, at least classically, you would say this is a theory where the kinetical induces spontaneous symmetry breaking. You see it once you do your Jacobian, once you do your field transformation, but definitely does not become a free theory. So the Jacobian in general is not an unimportant part it can be actually a part that contains a lot of the physics. That was why I used this simple example. Now, the next step is relatively straightforward. If you have k-dependent field transformation, they induce you correction terms in the flow equations. So the macroscopic field transformations, there the corrections are simply due to a simple change of the variables, which are kept fixed in the flow equations. That's pretty straightforward. If you have the microscopic field transformations, then the corrections are due to the k-dependent Jacobian, as I will demonstrate a little later. Importantly, for linear field transformations, the macroscopic and the microscopic field transformations are equivalent. So there is no Jacobian, there is no difference. The correction terms are identical. And now, in practice, actually, if you do not go very far away from linear field transformations, or if you have a certain class of nonlinear field transformations, then actually the microscopic and the macroscopic nonlinear field transformations, they give almost the same thing. And Holger Gies, who was who did the pioneering work on all that, I mean, that was pretty clear from the beginning when we started different versions of field transformations, and there was not a big difference. But in general, there can be a difference. So often does not mean always. Actually, the most powerful version of this field transformation is something that I will not cover today. The most powerful version, in my view, is that if you keep fundamental and composite fields, so quarks and mesons, if you want. I do not cover it in this talk because that's not used very often in gravity, and gravity usually use field transformations only without really going directly to composite fields. I refer you to work by Holger, Jan, and Stefan Flörchinger. There's a lot of work, and this is actually really pretty powerful. Has a disadvantage that, of course, if you have two fields, then you have, in general, to go to a more extended truncation because additional invariants become possible. So that will be the part not covered by today's talk. Now let me explain a bit more the macroscopic and microscopic field transformations. We start from a functional integral for the flowing action, and I use here the implicit functional integral definition of the flowing action. So you see it's given by the log, and then you have a functional integral over chi, you have the classical action, you introduce the usual quadratic cutoff term, and then you have here a term that involves d gamma over d chi. This is the macroscopic field times chi prime minus chi. So here you recognize the source term, and here you recognize the term that is usually related to the Legendre transform. This implicit differential equation on this definition by a functional differential equation, it has a big advantage. You do not have to go through explicitly through steps like Legendre transforms. You can just look at a given functional integral and compare the different versions and immediately realize if two things are the same or are not the same. So as you all know well, you can derive from this functional integral, you can derive the usual exact flow equation. Now, if you use macroscopic field transformation, this is only a variable change. This is very simple. You have not the macroscopic field chi kept fixed, but a composite field phi that may depend on k and on chi kept fixed. And then you just have to transform the flow at fixed chi to the flow at fixed phi, and that gives you an additional term. Now you may call this here the renormalization kernel for this macroscopic transformation gamma tilde k. It is just the logarithmic derivative of phi with respect to k. So That's pretty simple, and that has been often used, for example, for deriving the scaling equation for solving for fixed points and scaling solutions for functional flow equations. The important property, this macroscopic field transformation, that is what is usually related to field relativity. That simply says that effective actions that are related by macroscopic field transformations, they are strictly equivalent. And in particular, when you transform your macroscopic metric, you may have different geometries for the same physics. And I think you have all seen already this little Weyl transformation where the Big Bang is then transformed to some geometry with shrinking universe or something like that. All this field relativity is simply rooted in the equivalence of an object when you perform variable transformations. Now let's go to the microscopic field transformations, those that Jan has derived first and then later have been used for proposing the essential RG. If you write down again, first of all, I give you this field transfer, this microscopic, the correction terms for this microscopic field transformation in a form where you know it. You see already that there is again a term that is the gamma or the phi, now with a different renormalization kernel. And you have an additional term that involves the phi dependence of this renormalization kernel. And if the renormalization kernel is, of course, just a constant, then this part would disappear. That is what happens for the linear field transformation. So how to get this flow equation? Well, we can start again from a functional integral for the flowing action. And you see it's almost the same of what we had before, that there's only one important difference. In the cutoff term and in the source term, there is no the composite field appearing. So it's now a bilinear in the composite field, and it's then the source is given by the derivative of the effective action or the flowing action with respect to the composite field. Whereas the functional integral is still done by the original fundamental field. So we did not change the classical action. We have the original field, but we have now a cutoff that involves the composite fields and the in the source term that you have for composite fields. Now from here, it's again easy to derive an exact flow equation. It has the standard term, and then there are two terms related to the k-dependence of phi prime. So this is nonlinear field transformation. Phi k depends nonlinearly on chi. So you have a k-dependence of this field, and you have an additional term when you take the k-dependence here, that is this term. You see there are expectation values here. Expectation values are just taken with respect to to a weight factor e to the power minus f, where f contains now all terms in the action, which means the classical action, the cutoff term, and the source term. Now, with this type of expectation value, the so-called RG kernel is nothing else than the logarithmic k-dependence of phi prime at fixed chi. And you can use this identity for the phi derivatives of an observable in order to transform the flow equation to the form that you usually have with your correction terms. So that's all fine. These are exact equations. There is absolutely nothing else that has to be said to that at this point. Let's look, nevertheless, let's compare a bit the macroscopic and the microscopic field transformations. First of all, if you look a bit closer, the correction terms are different. So this is the t phi of x, that's the phi derivative, the k derivative of phi at fixed macroscopic field chi, where is the renormalization group, the renormalization kernel, the RG kernel, that's an expectation value. And then the RG kernel also appears in addition to dtrk in the numerator multiplying the usual propagator. So there are some differences, not major differences very often, as I was saying, but the two are really different. You cannot transform one to the other. And you should also be aware that these are different flowing actions. So the flowing action for the macroscopic field transformation, that has not changed. For that, you just have different variables, different macroscopic variables that you use in order to, as coordinates for expressing your function. So, but for the microscopic field transformation, actually the flowing action is a different one. If you just compare, then here is the gamma over d chi, here is the gamma over d phi, and then the cutoff term has now composite fields. So there are different sources, different cutoffs, and it's simply not true that the object, the flowing action that you get by field transform, by microscopic field transformations, that they are the same as without the field transformation. You do a change of the sources, and only if at the end you go to solutions of the field equations, then of course the differences disappear. But whenever you compute correlation functions or whatsoever, you should be aware that these objects are not the original flowing action. There's something different, and the way how you finally derive correlation functions, even though you can do it, is much different for this microscope, for the object that you obtain by microscopic flow equation from the original one. Different correlation functions, different relation between observables and correlation functions, and so on. Now, why did I tell you that these microscopic field transformations are nothing else than, in a sense, the variable transformation in your functional integral? Well, let's go again to this defining functional integral. So we have the composite fields in the cutoff and in the source term, and we still have the original fundamental fields in the classical action in the functional integral. So there is no variable transformation that you have done at this point. But you could do one. You simply could do one. You can go to make the field transformations already here to phi prime. Then you just get a Jacobian. And once you have that, you are, in terms of the composite fields, exactly at the same setting as originally for the fundamental fields. So the only difference is actually, once you have it in terms of composite fields, that you do not have your original classical action, but you have now your classical action with the additional term from the Jacobian. And if you look at the k-dependence of it, then without the, if you just say, if you just neglect the fact that the Jacobian depends now on k, you would get exactly the standard flow equation. So the interpretation is that these additional terms, they actually arise from the fact that when you make a field transformations here and you get this S bar of phi prime, then the classical action will become k-dependent due to this field's dependence, to this k-dependent Jacobian, and that's where the corrections come from. So if you want, the Jacobian strikes back for the microscopic field transformations. You do not really get rid of it. And you also see that if you look at your relation between the classical action and the flowing action and at large k, so your initial value for the flow equations. there again, you will get the Jacobian. You see it in a simple way. If you have a linear measure, then you can transform your defining implicit functional integral in a simple way, where now the cutoff term just is bilinear and the fluctuations. If k goes to infinity, this is a Gaussian functional integral that becomes exact. You can then simply get that gamma chi is given by the classical action. This does not work anymore for the microscopic field transformation, because now you do not have this simple for a general measure. If your measure is linear in chi prime, but not in phi prime, in order to use this trick, you first have in one way or another to go to phi prime. And if you have phi prime, then you have again your Jacobian. And if you do all the calculations correctly, what you find is, I think by now, not so surprising, you get this Jacobian in your initial condition. Otherwise, you would really come, if I go back to my simple example of this field-dependent kinetical, you would say, okay, if you neglect now this Jacobian in the initial condition, you would again have the impression that you get a free theory, which is of course not the case. So I think this example with the kinetical really demonstrates very well that you have to be careful on what you are doing. Now, quickly, advantages and disadvantages of both versions, because I think that they both have their merits. And we should actually use both if you use them in a reasonable way. Advantages is for the microscopic field transformations is that you can adapt your cutoff to the composite fields. It gives you richer possibilities also for eliminating couplings. Disadvantage, you have lost the direct access to the fundamental correlation functions, and you have also the Jacobian initial conditions that may sometimes be worrisome, sometimes not so much. The important thing is the access to the correlation functions, and I will come to that in the second part of my talk. Now, for the macroscopic field transformations, you have less flexibility. For example, your cutoff is really in the fundamental fields. It's not in the composite fields. The advantage is that you still have the contact to the fundamental correlation functions if your field transformation is reconstructed. Now let me come to this importance of keeping control of correlation functions. Let me first go again to the microscopic field transformations and study a bit more the relation of this RG kernel to the correlation functions of fields. So we have seen the RG kernel is given by the logarithmic k derivative of the expectation value of the composite field. But this can become pretty complex. And if you want to express that in terms of composite fields, you get in principle arbitrarily high correlation functions. I'll give you again a very simple example. Let me take phi prime is chi prime plus some small part g of k times chi prime squared. So really something pretty straightforward, pretty simple. You can, of course, get chi prime phi prime. This has now a square root. This is pretty trivial. And now you can, of course, compute what is the k derivative of phi prime. This is the k derivative of g times chi prime squared. And then you insert chi prime squared, and you see chi prime squared is now a complicated algebraic function with square roots. And that's already the point which I wanted to make. It starts to be, if you really express now your RG kernels in terms of correlation functions for phi prime, so correlation functions for the composite fields, it's no longer a simple expression. It contains now correlation functions of arbitrary order. And that is a warning, because by this type of things, you can actually produce a lot of things or remove a lot of things. And you better think carefully of what you are really doing. For example, I give you another simple example, a warning example. You can, for example, completely transform away by microscopic field transformations or by the RG flow, the potential in a scalar field theory. So let me take a theory of a scalar field coupled to fermions. We know fermions induce a correction, induce a contribution to the flow of U. So typically something, if you expand phi squared and phi to the 4, they typically induce spontaneous symmetry breaking if the effects are strong enough. And now I can use a truncation where at the beginning I neglect the potential. And in general, you would then generate a potential from the fermion fluctuations. But now I simply choose for this truncation an RG kernel gamma that is cubic and fifth order in phi. It has this coefficient C, which is nothing else than the integral, the momentum integral over this simple function. So it's a finite number. And once you take this RG kernel, you find that you cancel completely the contribution from the fermions. What is the physics of it? Of course, if the fermions induce spontaneous symmetry breaking, you know there is spontaneous symmetry breaking. But now we have transformed, we have eliminated the potential from the flow. So there is no minimum of the potential where you could find spontaneous symmetry breaking. So where did it go? Well, it goes into rather complicated Yukawa couplings again. So all the information about fermions inducing spontaneous symmetry breaking is now in complicated Yukawa couplings. That's definitely not where you want to have it. Because as I repeat this slide that I had before, field transformations, they do not really remove the potential, they just move it to a sector where you actually do not want to have it. So you better think, is that really what you want to do when you do a field transformation? You should really think, in my view, much more about the issue, in which way can I have my physically relevant information in a sector that is easy to control, where I can relatively easily find good truncation, and be afraid of moving it to sectors where a priori you may not see it anymore, and then you discard the sectors, but where you can move really important physical fluctuations to other sectors. So my lesson from that is field transformations are really very powerful. But the important thing is the issue of truncations. Field transformations are exact, but meaningful truncations will always need an understanding of the relation between the flowing action and correlation functions, at least qualitatively. So you can formally, of course, say I define my flowing action by arbitrary, by just some prescription for a flow equation and boundary conditions, and then I choose my boundary conditions such that I start with a known action at short distances, and I say my flowing action at k equals 0. This is a quantum effective action. That's all fine. It can be done, but if you do not know what is the relation to correlation functions, it will be very hard to devise any useful truncation. So the real danger is when I'm saying sometimes it's too powerful, the real danger is that you are tempted to remove things to sectors that you have no longer in control, that you truncate, and it's the truncations that are actually the danger. The best thing that you can do with the microscopic flow equation, if you do not want to go to the two-field formalism, is still a possibility to integrate your your definition of the flow kernel. So this gives you a flow equation for your macroscopic field that you solve with an initial value where phi is equal to chi. So that's something that Jan likes a lot. In this way, you may actually be able to avoid the Jacobian for the initial value, but this is still only a relation for expectation values. It doesn't construct you the microscopic field transformation, and you still do not have any direct contact to the correlation of the fundamental or composite fields. It may be possible if your transformation is smooth enough to at least estimate it, but at least directly, you do not have this contact to the correlation functions. At this point, I conclude. Field transformations, they are indeed a powerful tool for functional flow equations, but I think you really need to care about control of physical properties and the relation to correlation functions. Otherwise, you can get statements like the cosmological constant is irrelevant and can be discarded. We all know that this is not the case, but where does it come from? It comes exactly from this type of, in a certain sense, carelessness of this idea that irrelevant couplings are not physical. And I think that is something that we really have to stay away from. Of course, you can remove them. You can remove them to other sectors. You can say it's only particular combinations that are physical. But whatever you do, your physical information is not removed by field transformations. Universality can help because you could say it's perhaps not so important which flowing action it is exactly, and the initial conditions are not so important provided it's in the same universality class. But it's not guaranteed that you're in the same universality class. And again, this requires some thought about really the relation between the flowing action and the correlation functions. And as a last little remark, I hope I have convinced you that there are really different versions of nonlinear field transformations, the macroscopic and the microscopic. They are not really equivalent. They have different flowing actions and different correction terms. So thanks a lot.
Thank you very much, Christoph, for the nice talk. And we do have time for questions. So if you have a question, please raise your virtual hand or put a comment in the chat. And actually,